Okay, so now let us discuss tutorial 3.1 part 1 question 2. So in this question, visible light. Okay, visible light ranges from 400 nanometer to 700 nanometer. So visible light is emitted from two sources X and Y, and assume the waves are coherent. And the waves travel towards point P, and they are going to interfere destructively at point P, where the path difference between the two light sources X and Y to point P is given as 1.5 micrometer. Okay, take note, destructive interference means the path difference between the two light sources is d sine theta equals to m plus half lambda. And this path difference, this is known as your path difference. The path difference is 1.5 micrometer. Okay, so to solve this question, we need to substitute the values of n and see under what condition lambda lies in your visible spectrum. And we know n is an integer value. So we start with n equals to 0. So if we substitute n equals 0, what we get will be half the lambda equals to 1.5 times 10 to the power minus 6 meters. So solving for this, we can get lambda to be 3 times 10 to the power minus 6. Okay, we look at the visible spectrum. So visible spectrum is 400 nanometer. So 400 nanometer is equivalent to 4.0 times 10 to the power minus 7. And 700 nanometer is equivalent to 7 times 10 to the power minus 7 meters. So if we compare the answer that we got, 3 times 10 to the power minus 6, right? We see that it is lying outside the visible spectrum. Because this is your visible spectrum. The lower limit, and this is the higher limit of your visible spectrum. So this lies outside the visible spectrum, so this is not what we are looking for. Okay, next, let's substitute the next value of m. Substitute m equals to 1. So we substitute 1 to here, what we get will be 1.5 lambda equals to the path difference 1.5 times 10 to the power minus 6 meters. So solving for this, we get lambda to be 1.0 times 10 to the power 6. And again, if we compare versus your visible spectrum, it lies outside the visible spectrum. So this is not what we want. Okay, next let's substitute m equals to 2. So if we substitute m equals to 2, that is what we get 2.5 lambda equals to 1.5 times 10 to the power minus 6. So solving for this, we find lambda to be 6 times 10 to the power minus 7 meters. So if we compare this versus your visible spectrum, yes, it lies within the lower and the higher limit of your visible spectrum. So this here will be what we are looking for, right? Okay, next, we substitute m equals to 3. So 3.5 lambda equals to 1.5 times 10 to the power minus 6 meters. So when we use our calculator, what do we get? We get lambda to be 4.2 times 10 to the power minus 7 meters. And again, yes, it lies within the visible spectrum. So this is another answer. And then we substitute the next value, m equals to 4. So lambda will be 3.33 times 10 to the power minus 7. So this now lies outside the visible spectrum. It's actually smaller than the lower limit. So it doesn't lie in the visible spectrum. So this is 1.1. So basically, there's only two answers, right? That is when m equals to 2 and when m equals to 3, it fulfills the condition where it lies in the visible spectrum and it causes disruptive interference, and it has a path difference of 1.5 times 10 to the power minus 6 meters. So the most common mistake is students, right, when they reach the first value where, oh, this here lies in your visible spectrum, and then they stop. Do not stop there. Continue, right, for the next value of m. Find whether the next value of m falls in your visible spectrum. If it does, then continue for the next value of m. If this now doesn't lie in your visible spectrum, the rest of higher orders will actually not be in your visible spectrum. So we have to stop there. Okay, so once we have regions that's not in your visible spectrum, we continue until we get a region where it's again not in your visible spectrum, then only then we stop.